The forging process is a fundamental manufacturing method used to shape metal through localized compressive forces. It begins with upsetting, where the starting stock, usually a cylindrical billet, is compressed along its axis to increase its diameter and reduce its height. This step ensures the material is properly prepared for subsequent operations. The next stage is punching, where a hole is driven into the hot workpiece to create a hollow center, typically used to produce rings. Following this, the material undergoes ring rolling, a precision forming technique in which the punched ring is rotated between a drive roll and an idler roll. This enlarges the ring's diameter while refining its wall thickness and improving its internal structure. Notching is then employed to create controlled deformations that help guide the material during the forging process. This is especially important when transitioning to progressive forging into a round shape, where the material is incrementally shaped in stages to reach a near-net round geometry. The next phase, step forging, introduces varying cross-sections or levels along the length of the part, ideal for producing shafts, axles, and other stepped components. Bar forging follows, where elongated bars are shaped under repeated hammer or press strokes to achieve the desired profile. This method can utilize both open die and closed die techniques depending on the complexity and precision required. Finally, progressive forging of the second half completes the symmetrical shaping of the part, ensuring uniformity and balance. Throughout these stages, the forging process improves the grain structure, mechanical strength, and fatigue resistance of the material. Forged parts are known for their superior structural integrity, making them indispensable in critical applications such as aerospace components, power generation equipment, automotive parts, and heavy machinery. The controlled deformation, thermal treatment, and refined grain alignment make forging a highly reliable and efficient process for high-performance metal components. Additionally, by optimizing material flow and minimizing waste, forging supports both cost efficiency and sustainability in modern industrial production. The M200 mill turn performs advanced turning operations on large and complex components with exceptional precision. Once the workpiece is clamped, complete machining is carried out without repositioning. The horizontal turning spindle delivers up to 87,000 Newton-meters torque and operates at speeds up to 1,000 revolutions per minute, enabling efficient cutting of heavy-duty parts. With swing diameters up to 2,000 millimeter and center distances up to 14,000 millimeters, the machine accommodates oversized aerospace or shaft components. The integrated sinumeric 840D control ensures optimal path control, Turning is seamlessly integrated with other processes using the B-axis swiveling head and automatic tool changes at any Z-axis position. Heavy boring bars and up to 90 tools are available in the disc-type magazine, allowing continuous and flexible turning operations in a single setup. Prime turning is a revolutionary turning method that enables efficient machining of wheel stubs using the Coroturn Prime Twin tool holder. Modern multitask machines are designed for comprehensive component machining, but they often suffer from slow tool changing times, reducing overall productivity. The Coroturn Prime Twin tool holder addresses this issue by allowing for quick tool changes, increasing machining efficiency. This twin tool holder can perform both roughing and finishing with a single setup, saving time and improving overall machine utilization. By reducing downtime and optimizing tool changes, prime turning enhances productivity, especially for challenging components like wheel stubs. The technology helps manufacturers achieve faster cycle times, consistent part quality, and more efficient use of resources, making it an ideal solution for industries that require high precision and productivity. This advanced tool holders boosts operational efficiency, enabling manufacturers to meet the demands of modern, high-performance machining environments. Schmiedewerke Gröditz produces high-quality forged products for mechanical and plant engineering. The process begins with an electric arc furnace that melts up to 50 tons of liquid steel using 100% sorted scrap. After smelting, temperature and alloy adjustments are made in the ladle furnace, followed by casting into blocks suitable for forging. The largest ingot weighs up to 76 tons. The forging process is carried out on a 60 meganewtons press with pre-forging and final forging operations. Heat treatment is done in calibrated furnaces, followed by quenching in controlled oil and water tanks. The components are then subjected to ultrasonic testing, including tensile and impact tests, and undergo further quality inspections. Finally, products are preserved, marked, and cleared for dispatch. Istanbul Airport is Turkey's largest and busiest airport, serving as a major international hub with advanced facilities and expansive passenger capacity. The base of the Surinen oval table is made from cast aluminum using permanent mold casting, gravity die casting. This process ensures excellent surface finish, high dimensional accuracy, and superior mechanical strength. Molten aluminum is poured into a preheated metal mold, coquille, filling the cavity under controlled thermal conditions. Once solidified, the casting is removed, trimmed, sanded, and optionally polished or painted, resulting in a durable and aesthetically refined base ready to support the iconic tabletop. At Luxfer CNC, the manufacturing of AFEU HD composite cylinders follows a precise and advanced process to ensure maximum performance and safety. It begins with tube drawing, where aluminum liners are formed to exact dimensions. These liners undergo ultrasonic inspection to detect any internal flaws. Next, the liner spinning process shapes the ends of the cylinder with high precision. After a thorough inspection, each liner is wrapped with multiple layers of carbon fiber using automated winding systems to provide high strength-to-weight performance. The wrapped cylinders are then cured in controlled ovens to bond the composite layers. Once cured, every cylinder is subjected to hydrotesting at high pressure to validate structural integrity. This rigorous manufacturing sequence, combining metal forming, non-destructive testing, composite technology, and pressure validation, ensures that each Luxfer AFE-UHD cylinder meets stringent international standards for compressed natural gas (CNG) storage applications. At ULA's 1.6 million square foot production facility in Decatur, Alabama, the rocket building process begins with precision and scale. This is where Atlas V, Delta IV Heavy, and Vulcan Centaur rockets are born. Construction starts with large aluminum plates milled by double gantry skin milling machines, reducing weight by 70% while preserving structural strength. These panels are formed into curved sections through brake forming and bump pressing, then anodized for corrosion resistance. The panels are friction stir welded into barrels, a solid-state process using frictional heat without filler material, creating exceptionally strong joints. Dome structures are welded to the ends of the barrels in a circumferential stir welder, forming the core fuel tanks. After pressure testing, tanks are coated with spray-on foam insulation, SOFI, to protect against extreme lift-off acoustics. The assembly stage integrates complex subsystems like wiring, engines, avionics, and propulsion units. ULA also manufactures Centaur upper stages with ultra-thin stainless steel, spot welded and stabilized by internal pressure. A new production line for Centaur V increases throughput and precision. Final stages are fully tested before being transported to launch sites in Florida or California via the RS rocket ship. This vertically integrated process ensures each rocket leaves the factory fully mission-ready and built to withstand the rigors of spaceflight. The process begins with the selection of low-carbon or alloy steel wire, supplied in large coils, with diameters ranging from 2 to 6 millimeters depending on the type of nail. The wire is fed into a wire drawing machine to reduce the diameter to the desired size, ensuring uniformity and tensile strength, around 500 to 700 megapascals. During this stage, the wire passes through successive drawing dies, lubricated with oil for the machines. After drawing, the wire has achieved the correct gloss and size, ready for the next step. The wire is fed into an automatic cutter, where a high-speed cutter cuts the wire into short sections, corresponding to the length of the nail, from 20 to 100 millimeters depending on the type. The cutter operates continuously, ensuring that each section is of uniform length, with a tolerance of only a few micrometers. These wire sections are immediately transferred to the nail head punching machine. Here, one end of the wire is pressed by mechanical or hydraulic force in a steel mold, forming a flat, conical, or special-shaped nail head as required. The large pressing force ensures that the nail head is sturdy, crack-free, and can withstand strong driving force when used. Next, the nail body is processed if necessary. Some types of nails, such as concrete nails or screws, are grooved, threaded, or patterned to increase grip when driven into wood or concrete. This step uses a thread rolling machine or a specialized cutting knife, ensuring the sharpness and accuracy of the detail. After shaping, the nail is passed through a cleaning tank to remove grease, metal dust, and lime powder residue left over from the wire drawing step. The cleaning process usually uses alkaline solutions or ultrasonic cleaning and specialized powders to make the nail surface shiny, ready for the protective coating step. Then the worker carefully screws the tank to avoid the nail being thrown when the machine is running. After the machine is finished running, A crane is used to lift the nail tank to another place so that the worker can use a broom to clean up the remaining scrap. The scrap is collected, classified, melted in an electric furnace, refined to remove impurities, and then recycled into standard steel wire. This recycled steel wire ensures the same quality as virgin steel, reducing resource consumption and emissions. The highly automated process allows the production of millions of nails per day with optimal efficiency, with little material waste. The entire process combines modern machinery, from wire drawing, cutting, stamping, to plating and packaging, demonstrating precision and efficiency. Lime powder in the wire drawing step plays an important role in ensuring the quality of steel wire, contributing to creating durable, strong nails that meet demanding industrial applications. The repair process of a Howden screw compressor includes multiple critical stages, among which double-end grinding plays a vital role in restoring precision and performance. After disassembly and cleaning, key components such as the male and female rotors, end plates, and bearing surfaces are carefully inspected for wear, scoring, or dimensional deviations. If the rotor face's end or thrust surfaces show signs of distortion or uneven wear, they are machined using double-end grinding. Double-end grinding ensures that both parallel faces of the workpiece, such as rotor ends or thrust plates, are ground simultaneously with high precision. The component is clamped between two counter-rotating grinding wheels which remove material uniformly from both sides. This technique guarantees superior flatness, parallelism, and thickness tolerance, critical for maintaining tight clearances in screw compressor assemblies. Grinding parameters such as wheel material, feed rate, spindle speed, and coolant application are optimized to prevent thermal damage and preserve surface integrity. After grinding, components undergo dimensional verification using micrometers and surface finish inspection. This precise material removal restores sealing efficiency and mechanical alignment, directly involving compressor efficiency, noise reduction, and longevity. Following reassembly with new bearings and seals, the compressor is dynamically tested to ensure it meets Howden's performance specifications. The Bechatronic CNC plasma machine is one of the best options for computer-controlled metal cutting. Offered in multiple models, the machine varies in size and maximum cutting thickness to suit different industrial needs. It features a hypertherm plasma source made in the USA, globally recognized as one of the top plasma sources. The machine includes a separate control unit with a large 19-inch display, providing clear visualization of the cutting design and operational details. Ideal for precision metalwork, the Bechatronics plasma machine combines high-quality components with user-friendly operation for efficient and accurate results. The bulk forming process involves various techniques used to shape components from solid billets or semi-finished products. These techniques include closed die forging, extrusion, open die forging, rolling, radial forging, and thixoforming. These processes are designed to create components with high strength, dimensional accuracy, and a refined surface finish suitable for demanding applications in vehicles, machinery, and other industries. Closed die forging begins with the induction heating of steel billets to approximately 1,250 degrees Celsius. Once the billets reach the desired temperature, they are sheared into precise sections using warm shearing. Subsequently, a robot positions the sections under a performing press, where mass distribution occurs in 2 stages. After performing, another robot transfers the performed piece to a forging press, where an eccentric press with a force of 8,000 tons shapes the final contour through preliminary and finish forging. Following this, excess material is removed on a separate press. The final step involves controlled cooling from the forging heat, which sets the required mechanical properties without the need for additional heat treatment. In cold extrusion, the process begins with round material or weight-accurate steel sections that are inductively heated to around 980 degrees Celsius under protective gas. After heating, a robot places the material into a die for single-stage, flashless forging. Once the part is forged, an infrared sensor verifies its removal. This step is essential for components such as differential bevel gears, ensuring their precision. The material then undergoes controlled cooling, which guarantees dimensional stability. The final step involves cold calibration to achieve the exact precision required for the gear teeth, ensuring they are ready for installation. Transfer forging, on the other hand, involves heating round material to the forging temperature and then shearing it into sections. The material is then transferred through a series of stations by mechanically controlled grippers in a multi-stage process. Each station shapes the component incrementally, such as a car stub axle, while ensuring minimal die angles for precision. At the end of the process, the component undergoes calibration to ensure it meets the required dimensional accuracy. Hammer forging starts with resistance-heated bar sections, which are transported via conveyor to an upper die hammer. The material then undergoes preliminary and finish forging, during which 2 components are produced from a single section. After this, the flash is removed, and while the material is still warm, the components, such as car hinge brackets, are bent, blasted, calibrated, drilled, and checked for dimensional accuracy. In crankshaft production, a steel section is inductively heated to the required forging temperature. The edges of the material are broken, and the surface is descaled. Then, finite element simulation is used to optimize the tooling sequence before the material undergoes preliminary and finish forging in aligned dies. Following this, flash is removed, and the crankshaft is transferred to a twister to adjust the crank throws to the required angles. Warm calibration ensures the final shape and dimensional accuracy. Random samples of the crankshaft are inspected using an automated coordinate measuring machine to ensure consistent quality across all parts. For connecting rod forging, the process begins with heated steel sections that are removed from the furnace and descaled. After pre-stretching, the preforms are descaled again using high-pressure water. The finish forging occurs on a counterblow hammer, where both die halves move toward each other to shape the component. Once the forging is complete, a manipulator removes the forged connecting rod, which is then deburred and drilled. In front axle beam production, a workpiece weighing over 100 kilograms undergoes mass distribution through rolling, guided by a manipulator over several passes. Once this step is complete, the preform is transferred to a hydraulic preforming unit for bending, which establishes the rough shape of the axle. A manipulator then places the preform into a forging die, where a counterblow hammer completes the final forging. The workpiece is then transferred to a trimming tool to remove any flash, and the final shape is achieved through calibration. A robot places the completed axle beam onto a conveyor for further transport and final inspection. Horizontal cold forming, by contrast, involves processing material at high speeds over a 5-stage sequence. This process is used to form components like starter motor shafts, and it is known for its precision and minimal post-processing requirements. The workpiece is shaped with high accuracy, ensuring it meets the required dimensions and is ready for use without the need for further treatment. Upsetting is a process where the workpiece is clamped between jaws in a 3-part tool. The material is then deformed by an upsetting ram, after which longitudinal and transverse flash is removed. Cross-wedge rolling involves heating billets and shaping them between two profiled rolls. This method is used for both preforming and producing finished parts in medium to large quantities. The process is flashless, which makes it cost-effective and efficient for producing a wide variety of components. This technique is widely used in industries that require mass production of components with consistent quality. Ring rolling is a process where a pre-forged and punched disc is radially and axially formed into a seamless ring in a rolling mill. Specialized tools are used to produce profiled rings, and a table rolling mill is employed for radial-only forming. This method is ideal for creating components like rings that require a high level of precision and strength. Open die forging, on the other hand, uses non-confined tools to shape the material through multiple forging strokes on hammers or presses. Auxiliary dies may be used for specific applications, such as producing a shaft with 2 journals. The process can handle extremely large workpieces, sometimes weighing over 100 tons. Hand-operated or automated manipulators, either rail-bound or free-moving, are employed to handle these heavy workpieces, ensuring they are forged to the required specifications. These bulk forming techniques play a crucial role in the manufacturing of components that are essential for various industries, particularly those that require high-strength materials and precise dimensions. Heated steel ingots are transported by manipulator to the 5,000-ton hydraulic forging press. Using a push-down mechanism with up to 3 1,700-ton cylinders, the upper die moves vertically to forge the ingot into round bars, flat bars, or near-net shapes. Cylinder usage is adjusted based on the material size and deformation resistance. For long products, intermediate reheating is performed in a 10-meter-long furnace during forging. The manipulator firmly holds and repositions the workpiece to ensure precise deformation. Forging continues through multiple strokes until the target shape and dimensions are achieved, accommodating parts up to 10 meters in length and 30 tons in weight. The TPA 200 hot extrusion press is used at the Volsky pipe plant to produce seamless steel pipes through a high-pressure forming process. The operation begins with the preparation of steel billets, which are cylindrical blanks with diameters ranging from 90 to 250 millimeters, lengths up to 4 meters, and weights up to 1 ton. These billets are first cleaned and then heated in a furnace to temperatures between 1,100 degrees Celsius and 1,300 degrees Celsius, depending on the steel grade, to reach a plastic state suitable for deformation. After heating, the billet is loaded into the container of the TPA 200 press. A powerful hydraulic ram then pushes the billet through a shaped die. For producing pipes, a fixed mandrel is inserted along the axis to form the inner cavity of the pipe as the metal flows around it. This results in the formation of a seamless tube with a circular cross-section. The extruded pipe exits the die at high temperature and is guided along a run-out table, where it is cooled with water. The pipe dimensions after extrusion range from 60 to 200 millimeters in diameter, with wall thicknesses of 16 to 55 millimeters and lengths up to 10 meters. After cooling, the pipe undergoes additional processes such as cutting to desired lengths, straightening, and heat treatment if necessary to meet final technical specifications and ensure mechanical performance. The TPA 200 allows efficient and precise production of seamless pipes used in demanding industrial applications.